Well, hi folks. Today we're going to talk about the Nyquist zones again, but in relationship to how can we use Nyquist zones when we're working with DACs, or digital to analog converters. So let's quickly go over our classical example here. We got a 1 megahertz digital sine wave being fed into our DAC there. Our DAC's running at a 100 megahertz clock, clocking away, clock, 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 clock. And then we're going to take the output of that DAC and feed it into a low pass filter with a cutoff frequency of 50 megahertz there. And I think it's pretty clear that we'll see a nice 1 megahertz sine wave on the output of that low pass filter. So this is your classical setup for how we would work with a DAC that would be running at a 1 megahertz clock. Well, what if we were to remove that low pass filter? Basically, I'm proposing this. What if we have our digital 1 megahertz sine wave, and you see that there on the left. Again, the DAC is still running at a 100 megahertz clock. And if we were to take the output of that DAC and put it to a spectrum analyzer, that's something that allows us to see tones, sine waves in the frequency domain. I'm asking, what would we see? Would we just see a 1 megahertz tone? Or would we see other tones? Well, we would see other tones. Again, if we took the output of the DAC and put it straight to a spectrum analyzer, we would see a 1 megahertz tone, we would see a 99 megahertz tone, we would see a 101 megahertz tone, we would see a 199 megahertz tone, and we would see a 201 megahertz tone. And maybe it would just keep repeating. We would see a 301 megahertz, a 399 megahertz. It would probably be much lower in power. But you can start seeing, we start seeing tones that are integrals or integer functions of the sample rate. And they all are centered around the sample frequency. So in our case, remember the sample clock was 100 megs. So that's why we're seeing these glumps of signals repeating at integer multiples of the clock. We see 100, 200, 300, etc. So these are what's called Nyquist zones. And we can use this idea to save us from needing to have mixers and local oscillators to shift the signal up. We can actually have the signal come out at a higher band right out of the DAC. And that is called Nyquist zones. But in our case today, we're focusing on how we use that for digital to analog converters. And here is a representation of the Nyquist zones. The first zone we could use is your classical one, 0 to half the sample frequency. That's a normal zone. Normal means it's not flipped or anything. The next zone is half the sample frequency to the sample frequency. Now if you wanted to use that zone, your signal or spectrum would be flipped. That's why I put a little F there to let you know that the signal will be flipped. Now the next zone is the sample frequency to half the sample frequency. That's another zone. And that will be a normal zone. So the spectrum will not be flipped. That's why I put a little N on top of it. And another zone you can use is 1.5 times the sample frequency to 2 times the sample frequency. And that zone will be flipped. In other words, your spectrum will be inverted. So in software or whatever, you're going to have to correct that. For those of you using IQ, you're going to have to flip the IQ in your digital IQ modulator. But these are the Nyquist zones or regions that you could pick out of the output of the DAC. And the idea being that you could pick a bandpass filter to center or pick what zone you want. Or you could have a bank of bandpass filters based upon what zone you want to come out at. So this is a very clever idea, and it's being heavily used now that we have DACs that have clock rates of 1 gig, 2 gig, even 3 gigahertz. We can start using this idea so that we don't have to have a bunch of mixers and local oscillators. We can just use what's called Nyquist zones to get the signal right out of the band directly. Ain't that something? So here would be an example. Let's say we would like the signal to come out at 101 megahertz. So we would feed a 1 megahertz digital sine wave into our DAC. Again, our DAC is running at a 100 megahertz clock. And then we would pick a bandpass filter here, and it would be from 100 megs to 150 megs. And if we looked at the output of that bandpass filter, we would see a sine wave that's at 101 megahertz. So that's how we got a signal up to 101 megahertz, strictly by taking advantage of the Nyquist zones of the DACs. Now again, to do this, the critical component becomes the bandpass filter. Has to be a very good bandpass filter and have no very low side lobes so that none of the other bands get through. And the other trade-off is the power level out of the DAC in these Nyquist zones is generally going to be lower. So you're going to need some amplification. But this is an idea that's heavily starting to be used now that we have DACs running at a much higher clock. And I would just figure I'll show you folks how to use it. So now you can make all kinds of fancy jammers out there using DACs. Well, this is Moonshine Radio. Thanks for watching.